All right, let's continue with what we're doing. So last time I showed you how having this Galois group allowed us to move prime ideals around above a certain prime P. And this also is going to tell us about what are the possibilities for primes that ramify in my field. And there's a link between primes that ramify and the discriminant. And we're somehow going to see one half of this link in the following theorem, which is 3.6.9. And it goes as follows. So let P be a prime number. And K a number field. Then if P is ramified, in your ring of integers, then P divides the discriminant of my number field. And the converse is true, but we're not going to do this because the proof is a little bit more complicated. But this half we can do with what we've done, and we'll use at some point. We're going to use at some point this Galois action that we have. So because we're assuming the prime is ramified, I'm going to take one of the primes, the prime of all which is ramified. So let P be a prime ideal. In OK, such that the ramification degree is greater than 1. Then if you think of writing write this prime ideal P as a as a product of prime ideals, you're going to get this P to some exponent, some number greater than 2. Let me just call this E. And then we're going to get all the other prime ideals showing up here. And so I'm just going to write this in a specific form. I'm going to take one copy of P and put it here, and the rest I'm going to call A. So writing the ideal P as P times A, where A is divisible by every prime ideal over P. It's indivisible by all of these prime ideals of P. All of these ideals are contain the ideal P by this division inclusion thing. So I'm going to just write my factorization like this, which I can do this. This is going to be divisible again by P because I'm assuming that my prime is ramified, so this shows up to exponent at least 2. So this E here is at least 2. That's bad. Just put E. I will call E. It's just E. Like this. So I can do this, and I'm just going to study this ideal A. So where A is divisible by this. So let's start by picking a basis for my ring of integers. So I'm going to let alpha 1 to alpha n be an integral basis. For OK, whatever this basis is. I don't need to find it explicitly, but just take one, know that it exists. Since A is properly contains the ideal P. That containment is proper because I've taken out this factor of P, so A divides P, which means A contains P, but it's not the whole thing because there's this prime P missing. So since A properly contains P, we can find some random alpha, not this integral basis, but just a random element alpha, which is in A, but not in the ideal, not in this ideal P. Then we can write, I write alpha out in terms of my basis. So I write alpha is say alpha 1 m1, alpha n mn. I guess here implicitly n is the degree of my field. But it's not a huge deal. We're not going to use that. So I write my my alpha in terms of my integral basis, where these obviously these mi's are not, because it's integral basis, these mi's going to be in z. Since alpha is not in the ideal generated by p, then not all of the mi are divisible by p, because otherwise it would be in the ideal generated by p. By p, so at least one of them has to be not divisible by p. So without loss of generality, without loss of generality, we can assume, just by relabeling, assume say p doesn't divide the first one. Now, similar to what we've done in one of the previous propositions, which somehow we saw how changing two different bases changed my discriminant. So we can compare what happens when I change in my basis, say alpha 1 for alpha. So similar to proposition 2.2.4, we have that the discriminant. So just go back and look at the proof of this proposition. You see that the discriminant of this set, so alpha. Alpha comma alpha 2 all the way up to alpha n is the same as m1 squared times the discriminant of alpha 1 now to alpha n, our original discriminant, which is m1 squared, the discriminant of my number field, because it's the discriminant of my basis. I define delta of OK to be the discriminant of an integral basis, and I proved to you that the discriminant of an integral basis didn't matter what integral basis I had. And I don't know that this is an integral basis, so no, this is m1 squared, and I guess this isn't an integral basis if this m1 is going to be non-trivial. So since I'm assuming that p doesn't divide m1, since p doesn't divide m1, it's enough to show that p divides this discriminant, the discriminant of alpha 2 for comma, because I have this equality, right? I have I know that p doesn't divide m1, so p has to divide, and I'm assuming that if I can show that, so I know that p doesn't divide m1. If I can show that p divides this number, then p doesn't divide m1, so p has to divide this number, which in particular means that p has to divide the discriminant of my number field. So it's enough to show that p divides this thing, and this is sufficiently nice to where we can study the prime ideals, and I'm just going to essentially show you that for every prime ideal above p, they contain alpha, so this discriminant has to be somehow divisible by p by just considering what the prime ideals show up in this factorization, essentially. But we'll get there slowly. So let's. I've been talking about this using this Galois group on it. So this is where it's going to come in. So I'm going to let sigma 1, sigma n be the embeddings of k into complex numbers. I haven't assumed, as you notice in my theorem, that my field is normal, but this isn't a problem, because I proved to you that I could always extend my field a little bit to make my field normal. So I'm going to let L over K be a finite extension K such that L over Q is normal, which I'll remind you exists by proposition, what's it? What was it? Proposition 3.6.4. So I showed you I could always make my field a little bit bigger and get it. And I'm going to let now G be the Galois group of this normal field. So maybe the Galois group of L over Q. Then the elements of G, what are they? They are embeddings of L, which keep K fixed by definition. So the elements of G are just embeddings of L which extend the embeddings. Okay, sorry, maybe I said this wrong. They're not embeddings at fixed K, because this is the Gauss group of L over Q. So these are just embeddings, but because L lies over K, these are going to be somehow extended. You know, we saw how when embeddings we could go to like an intermediate field and how they extend it. So how many ways there was to extend an embedding from an intermediate field up to top field. So each of these embeddings will be an extension of an embedding of K. Just if you don't remember what this means, go back and look at the previous definition, like 1.5.5. That should tell you, remind you what embedding extension means. So let's go back and think about alpha. Since alpha is contained in this, remember this element alpha, which I took some element alpha, which is my ideal A, but not in the ideal P, which I could do by my construction. So since alpha is in A, it's contained in every prime ideal. In OK over P. Recall that A contains every prime ideal over P. So if it's contained in here, remember I'm saying that A factors the product of prime ideals. That means that A is contained in each of these prime ideals. P dividing A means that A is contained in P. So if alpha is an element of A, it means it's contained in every prime ideal over P. So it follows that. So, but this was I'm talking about in K. It follows that the same thing happens in L. That alpha is also in every prime ideal over over P in OL. My other ring of integers, since why is this? Since such a prime ideal, let me give it a name. Say ideal. Say such a prime ideal beta L. Contains. It's going to contain the number P, and beta L intersect with OK is going to be some prime ideal, say PK, which is again a prime ideal containing P. But now in OK. So I know that whatever the prime ideal over L is, I know that when I intersect it with K in the middle, I know that this contains alpha. So the top one is just a bigger prime ideal, so it's obviously also going to contain alpha, essentially. So it also contains alpha. So it also contains alpha. Contains P, which is again containing P. Let me see. So therefore, also contains alpha. So alpha is in all of these prime ideals, these beta L's, whatever, for every prime above L. I'm sorry, for every prime above P, prime ideal above P. So now let's fix one. So fix beta L, a prime ideal LL over P. Then what's my claim? Claim that for all sigma in my gamma group, I have that sigma of alpha is in beta L. I claim that all of my embeddings keep. I know that alpha is in one of these, but all of the embeddings stay inside this prime ideal. So to see this, note that if I look at the inverse sigma alpha of beta L, this is again a prime ideal in OL over P and contains, so by the above, it also contains alpha. So if sigma inverse of beta L contains alpha, then that means that sigma of alpha is in beta L. So contains alpha. Particular, what does this mean? I took a random one. Particular. This means sigma I of alpha is in beta L for all I. Remember, these sigma i's were, or was this? Sigma i's were my embeddings of k into C. So I gave the names for the embeddings of sigma into C. And because the embeddings of L into C are just extensions of the embeddings of k into C, so they contain the ones in k, then this also is true for the embeddings of k. So all of these are in here. But since the discriminant, now I'm just going to go back and use the fact that the discriminant is an integer. Since the discriminant is an integer, we have, what do we have? So if you think of how you compute the discriminant using the embeddings, you'll see the following. Well, okay, sorry, I skipped a line here. Let me read this slowly. So sigma I contains this beta I for all L. Therefore, by proposition, what is it, 2.2.17, which told us how to compute a discriminant in terms of embeddings, we see that was the one that this proposition was the one that said like the discriminant looked like sigma i's of alpha minus sigma j's of alpha squared, and you have some product over I is less than j, blah, blah, that gave you the discriminant. This is what this proposition was saying. So every element, basically every element in this formula for calculating the discriminant looks like some sigma I of alpha, and because they're all contained in beta L, so this means that this discriminant sigma alpha, comma alpha 2, comma alpha n, this is some element of beta L. But now, since this is a discriminant, and we know that discriminants of, if I take a bunch of algebraic integers, the discriminant that I get is an integer. But since this discriminant is an integer, you see that this element, this thing, this has to be contained in beta L intersect Z, which moments of thought, will tell you, because these are all prime ideals over Z, this is just the ideal P. Therefore, P divides this element. Alpha, not alpha J, alpha comma alpha 2, alpha n. And we're done, because all I need to check, all I was saying is, well, I can check that P, if I can check that P divides this number, then it means that P divides this side of the equality, but I know that P doesn't divide M1 squared, so P has to divide this number, which is exactly what the discriminant of my field is. So if my prime P was ramified, then I had to divide the discriminant. Cool. So here's a simple corollary of this. 3.6.10. So let K be a number field. K is isomorphic to Q alpha for alpha some primitive element. And I'm going to let F be in some polynomial in Z of X, which is monic, and such that F of alpha is 0, so it could be the minimal polynomial, but it doesn't have to be. Then if P is a prime number such that P doesn't divide the norm from k to q of the derivative of f by the derivative of alpha, then P is unramified. So you can use the above theorem to tell us when things aren't ramified. So to prove using f instead of the middle polynomial is somehow a red herring. That somehow the middle polynomial will divide f, so it's not going to make too much difference. So since every monic polynomial with alpha as a root is divisible by the middle polynomial, it's enough to check this for, just think of for f equals m of alpha. Think of it, if f was m of alpha times something else, then it will just come out in the norm. So you'll have the norm of the f primed of alpha, but there'll just be a product of two things. So just have a think about it, and you'll see why it's the case. So I might as well just take f to be my m of alpha, but then proposition 2.2.19, which related this number to the discriminant and the previous corollary. What's it? Corollary 3.6.9. Give the result. Essentially, P doesn't divide this. This number is related to the discriminant, so P doesn't divide the discriminant. So by the previous result, P couldn't have been ramified, so it has to be unramified. So here's another corollary of this, 3.6.10, which tells us that there's only finitely many primes that can ramify, and that's clear because the discriminant can only have this prime number. It only has finitely many prime factors, so there's only finitely many possibilities. So there are only finitely many primes of Z which ramify in a number field K. Okay. And lastly, the last thing I want to do before moving on to how to use all of this for cyclotomic fields is tell you, come back. I mentioned ages ago when I did this splitting of primes in quadratic fields. I told you how to factorize these ideals generated by primes in quadratic fields completely. There was one bit of the theorem which I didn't prove, which is what I'm going to come back and prove now. So this is corollary 3.6.12, which is the following. So I'm just going to use notation 3.7 and 3.9. Go back and check of theorem 3.5.17. The ideals are distinct. So I can go back and show you the result. Where was it? This was a while ago. Here we go. I had this theorem which told you that if you have a square root integer and you looked at k square root n, it told you how the primes, without having to do much thinking, it told you how to factorize the prime p into prime ideals and so on. And I, in these two cases, in this one and this one, I never checked that these two ideals were distinct. This was one of my claims. So moreover, in 3.7, 3.9, the ideals are distinct, and I told you we will defer this proof to 3.6.12. So this is what I'm coming back to do. And essentially, the proof is, well, if these two things weren't distinct, then this thing would be ramified. But I'm just going to tell you in these cases, the prime couldn't have been ramified. So let's go all the way back. So we have this. So using what was it? Exercise 2.2.28 and theorem 3.6.9. We see that in each case the prime does not divide the discriminant. So this exercise was the one which calculated the discriminants for quadratic fields. So in each case, the prime does not. The discriminant, delta of, say, q root n. So they can't be ramified. So P can't be ramified. So ideals must be distinct. Cool. All right. So next time what I'll do is I'm going to use all of this Galois theory and somehow combine this with this Dedekind Kumho result, and I'm going to essentially tell you in cyclotomic fields how primes factor in basically a complete description of this.